Hello everyone, my name is Brijraj Singh. I'm from on-device AI team of Samsung R&D Bangalore, India. I worked on this paper with Yash, Mayuk and Praveen. The title of the paper is a framework for asymmetrical DNN modularization for optimal loading. As we encounter with several DNN powered applications in our daily life, if we take a typical case of a prediction through DNN model, we see that a sample is taken up onto the device, and that device has to perform two tasks basically. One task is to load the DNN model onto the working memory. Second task is to perform the inference with that model, right? And the task could be classification, segmentation, detection, or any other predicting task. So these two process actually imposes two latencies into the end-to-end responsiveness of a model. So T total is the T loading and the T inference. We are particularly targeting here with for reducing this loading latency, right? There has been a lot of work with this inference latency, and people have been proposing the solution for optimizing the model, compressing the models to have a lower number of the floating point operations so that inference can be improved. But here, this is kind of there are very few work which actually deals with the loading the time, reducing the loading latency, and this is one of it. So idea says that if we are having 100 layers, one DNN model, right? So if we could segment it down among 4 child models, each with a 25 layers, right? So we can, and if we try to load all of them in parallel rather than loading one big model of 100 layer, we will be loading 4 child model of each with 25 layers. On that case, we can utilize the hardware of device, which says that it is having 4 hardware threads, right? So all the one thread can be delegated for loading one model. So 4 threads will be working for loading 4 models, right? In that case, we could reduce the latency for loading the model, right? Take a particular example here, like if a model is having several blocks, like n blocks, each block is having some set of layers, then we want to segment it down to the child models of maybe k child models, each with having a position vector from 0 to p1 for child model 1, maybe p1 to p2 for child model 2, and so on, right? So this way, this ith child model, if we represent it by mi, then that will have the block pi minus 1 up to block pi, right? Here we want that all the child models should have equal loading time. If that will be attained, on that case, the effective loading time of the full model will be equal to the loading time of any of the child model. By considering this, we also see that there are one additional advantages in this case, that the last child model will keep the gradient true. By keeping the gradient true for the last child model will facilitate us for putting it for personalization. Whenever we'll be requiring the on-device personalization or on-device training, we need not to touch any of the child model except the last one, right? So this reduces the effort required for on-device personalization. So the proposed approach says that a vendor comes with a model M and the device. Then we put it to the RLU unit, and that RLU unit converts that model M to M dash, whereas the expectation from M dash is that the loading time of M dash will be lesser than the loading time of M. Okay, and we go to see what is the RLU. So the proposed approach says that in a typical example of processing through a DNN model, which involves the first process of loading the DNN model from the auxiliary memory to the working memory, we have been loading the full model as of now. Instead of loading one big model, we'll be loading the several child models in parallel. So this parallelism will provide us the facility, will provide us the lower or the lesser loading latency, right? If we go to the next in the detail with the reinforcement learning unit. So the reinforcement learning unit, we see in the previous slide that here we have splitted this one child model to one big model to 3 child models. So we have to take the decision about in how many models, child models, we should modularize it, right? Lesser model or the more child model may not be able to provide the best loading performance, right? So this decision has to be taken, and we are delegating this work to the RLU unit. This work has been done from by RLU. RLU takes into account the given model and the device stats. It starts with the controller process, which takes a decision on the K and the P, where K is the number of the child models and P is their corresponding position into the big model, into a main model, right? And this decision are given to the splitter, where a splitter splits the model as per K and the P, and the number of child models are generated, which are loaded on device, and the performance is evaluated. The evaluated performance is sent to the controller as a feedback, which is a reward in sense of the reward, and on the basis of this reward, the controller improves the decision, and the better K and P is predicted. Right, so this keeps going on unless we attain the good performance. So the main crux here lies that it's not only the case that if we are having 4 threads available onto the device, then for decomposing the model, big model, the big given main model to 4 child model will give the best performance. That is not sure, because the system stats may vary at that moment. That would be the case, like all the 4 models maybe are exploiting with the one of the hardware thread. So other binaries and miscellaneous files may not be able to get loaded onto the working memory. Because of that, so it will demand some other time, and that will be a sequential time. So it will increase the loading latency. In other cases, that if you it will be lesser ambitious and will have just 2 models, on that case we may not be able to attain the best performance of this proposal, right? So somewhere we need to trade it off so that we can attain the best performance, right? A typical iteration of RLU happens to be is like take the model and the device states into account. Controller takes the decision. That decision is given to the splitter, takes the performance, evaluates the performance, and the reward is set. So reward comes with 2 values. Reward could be 0 if tau is equal to t by c split plus minus epsilon. That says if a big model is taking 200 millisecond of a loading time, and if you are having decomposing it or splitting it among 4 child models, then each child model should have taken 200 by 4, that is 50 millisecond, right? So if it is taking value somewhere plus minus 50 millisecond plus minus epsilon, on that case reward will be 0, otherwise reward will be negated. We want to have this kind of a performance. Okay. So let's get down and see about what is the best case here. So normal case says that the existing case says that we are having hardware threads, we are having one model, and it takes the time t for loading them, right? There could be 2 cases. 2 cases says that if we are having hardware threads at 6, we could have the 4 splitting or we could have the 6 splitting. What happens if we are having 4 splitting? So we are having 4 child models out of one M given DNN model. So what happens is like all the child models are loaded in parallel, whereas there is no thread left for loading the miscellaneous file. No, so the threads are left for the loading the miscellaneous file because we are having 6 threads, right? So the leftover threads will be working for loading the miscellaneous file, and 4 will be busy for loading the 4 child models. Okay, so that is the case, and it takes t by 4 plus minus delta time. What happens if you would have split it down among 6 child models? We are having 6 thread. All the thread is now loading one model. So what happens that binary or the miscellaneous files cannot be loaded because there is no leftover hardware thread left, right? So it will be loaded on the next time quanta. So this time quanta will be in a sequential. When this loading will happen, then second time this loading, the loading of the miscellaneous file will happen. So additional because of this additionally added the sequence, the time, and the overall latency time will be more than what we were attaining at t by when we are having 4 decomposition, right? So here also it says that the best splitting is the good splitting minus, overhead. So the additional overhead for this sequential timing will be reduced if we could have got the better decision about the number of the child models. However, any of these attempts are made to attain the best performance, whereas even the wrong decision is taken, then also the time taken for the loading one model will always be higher than with the time taken by for two model, right? So in any case we will be able to achieve the better performance from loading just one model. Okay. So the second claim says that whenever we'll be segmenting down the full DNN model among child models, so if this is a child 1, this is a child model, this is a k minus 1 child model, and this is, for example, kth child model, which is the last child model. So we will keep the gradient live for this child model and we'll set the gradient false for the rest of them, so that this child model can participate in device learning, on device learning, and that happens for personalization, right? So we need not to be worried for about controlling the gradient at the time of fine tuning on device. So this will provide other features of maybe like the gallery model, which was not able to, which was trained with certain events and was doing very well. Now a certain new event comes, so model is now having the ability of learning these new events. So it will identify it as a new event, and it will learn it for future tagging, and in the future it will identify that this has been a event in our phone recorded maybe the previous time. So we see that the proposed system at a glance. Processes are shown as a one by one steps. So P1, P2, and this graph shows the parallel and the sequential process. The process initiates when the vendor provides the DNN model along with the device at P1. At process P2, this stats, device state and the model architecture is delegated to RLU block. At time t3, at process t3, at the time t1, this RLU blocks decomposes or splits or modularizes this main model among k child models, whereas n child, if there are n hardware threads available, then at process p4, n child models will be loaded and rest of the models will be waiting in the waiting pool at process p5. Next, at time t2, after delta time delay, the the child models which have been there onto the loaded pool, which are already loaded, now they will be delegated for the inferencing, and rest of the models which were there in the waiting queue, they will be loaded onto the working memory, right? So this process P6 and P7 will be executing in parallel, right? The loading and the inference. When the loaded models are delegated for inference, the rest of the child models will be in loading, right? So that way, this is attaining reducing down the performance in some sense, right? Next, when this happens, at process P8, the device model and this loading scheme is being bundled up and is given to the vendor at process P9. So you can see that few of the processes are executing in parallel, few of the processes are executing sequentially. So we have performed this experiment in Samsung S20 device with the ARM-NN platform. We having a TensorFlow.pb frozen file, right? So when we checked it with the software ISP model, MobileNet V1 and the MobileNet V3, we realized that there's a huge performance gain with this approach. There's a 60, 58, and a 55.2. So these are the corresponding indexes in a main model, right? The same experiments we performed on the PyTorch environment with NVIDIA GPU and taken several instances of this experiment. So on an average, we could see that in bigger the model, the better is the performance. Like in Inception V3, we could have reduced it down up to 83.14%, whereas the SqueezeNet, we could reduce it down up to 18.63%, right? So in all the cases, there was the performance gain we have noted it down. You can see that this is a process in this work. This process proposes a method for improving the loading latency of a DNN model without affecting the inference performance. The proposed method follows a device-dependent approach in order to attain the maximum benefit on device. The work targets improving the user's experience while interacting with the DNN-powered apps on edge devices like mobile phone, smart TV, etc. This way, the work opens a new direction of research in DNN operations. Thank you.